So we have this function. We want to show the shape of the graph near each of the listed points. And let's see why we do this. Okay, we have now when you graph this function, what are you going to do? The very first thing is you're going to find the zeros of the numerator and denominator. That's very straightforward. And these 3 points are the first 3 that I wrote down here. Okay, so if you see a problem like this and I ask you to do something mysterious with it, then I say, well, if you can't do that, go ahead and just construct the graph. Well, if you start to construct the graph, you're going to identify these points. First thing you're going to do. The zeros of the denominator are range, probably not registering properly. We have -6, not 0, 6, but 6, 0, -4, 0. So I wrote that down carelessly. So we have 6, 0, -4, 0. Now, these pictures that I have here, I have a separate picture. I have a picture for x equals 3. I have a picture for x equals -2. I don't have the picture for x equals 1. Okay, that would correspond to this 0. But you would be a little bit proactive, you would add that. And maybe not. If you just do the ones I have here, it's going to be okay. But then you got 6, 0, which corresponds to x equals 6. Right there's a point 6, 0. Here's your x equals -4 line. Right there's a point -4, 0. Those are key points. Well, then at 3, 0, could write this as all this stuff multiplied by x -3, right? So if x is equal to 3, then you can plug in 3 over here. I think you're going to get 25 times 2, which is 50, divided by -3 times 7, -21. You could actually say at x equals 3, you get this, which is just a vertically stretched x -3 function. Near that 0, this number isn't going to change very much until you move a little ways away from that 0. So it's like you have a vertical stretch and reflection. So the graph is going to look like this. something like this. Maybe it's steep, maybe it's not that steep. Okay? Gonna look something like this, or maybe steeper, maybe less steep. The point is, it's going to be pretty close to linear. Now, you know, from the way these functions behave, this thing's going to move away from linear. It's going to start curving. But if you look very, very close to the x equals 3 point, it's not going to have much curvature because this number is not going to change. If you go to negative 3 point, or to x equals 3.1, that's going to change what all these things multiply out to. Maybe instead of like 2.5, it's 2.4 or something like that. It'd be very close to a linear function. And if you want to understand graphs and understand these functions, it's kind of important to understand this. Okay, so I can say near okay, at 3, 0, this is what you get. Near 3, 0, you stay near this for a little while before the other factors start causing you to curve away. Okay. At negative 2, 0, we can write this function as y equals x minus 3 times x minus 1 over x minus 6 times x plus 4 squared times x plus 2 squared. At x equals negative 2, this is y equals, that'd be negative 5, yeah, and negative 3, which is 15. The denominator would be negative 2 minus 6 is negative 8. Negative 2 plus 4 is 2. To square that, you get 4. Multiply that by 8, and you get 32, but that's negative because the x minus 6 gives you a negative. Actually, the x minus 2 gives you a negative, and this gives you a negative, and this gives you a negative. Yeah, I think it's negative 15 over 32. So near x equals negative 2. Well, what would the graph of negative 15 30 times x plus 2 squared look like? It's a horizontally shifted squaring function with a vertical stretch and a reflection around the x-axis. Which means that the function, if I've done my arithmetic correctly, is going to look like this. There's something that may be kind of wrong about that. Maybe I've got it upside down because maybe I didn't do my arithmetic carefully enough. Okay. That really is a plus 15 over 32. That would be up like this, but it's going to be a parabola with its vertex here. So again, now I'm writing things out and explaining these things to myself. Okay. And as I keep urging, you need to do the same. Had you been taking a little extra time on your homework and finding out what you're doing, you would have explained it to yourself enough times that everybody probably would have done better on the midterm. Okay? And we want to work toward everybody doing better on the final than they would if they didn't explain things to themselves. So as I keep kind of nagging you, you're not writing it out the way I'm writing it out. You're not explaining it to yourself in a way that's going to stick with you. Well, you're doing it by habit, you're doing it by imitation. And that's something, I mean, you know, at some point you do that. But your insights to be gained by finding out why you're doing what you're doing. Okay. Now we're kind of out of board space. So move on here. And, you know, we could do the 0.10. I'm not going to do them all. So I'm going to switch over here. I'm saying now, well, the parentheses around this, and then it's times 1 over x minus 6. That's approximately equal to, if x is 6, you get 3 here, you get 8 squared. 8 squared, 64, 3 times 64 is 192. And then you're getting 5, and 5 times 192 is 960. Everybody knows that. Okay? Now, maybe I'm right, maybe I'm wrong. X plus 4 squared is fortunately easy. It's 100. So you're getting approximately 9.6 times 1 over x minus 6, which is it's a toolkit reciprocal function, vertical stretch of 9.6, horizontal shift of plus 6. You know, you might not understand it's important to write out what I just wrote out there, but it is. Because you're emphasizing the fact that it's not exactly equal to this, except at this point, but it's near this. So if we write out, because get this reciprocal function, here's x equals 6. Your reciprocal function is going to look like, well, that was a bad. Okay. Now, I'm not going to write out all the details. Good. Putting 3 dots now, look to be all the details I've got here. Y equals something times 1 over x plus 4 squared. What's the something? It's what I get when I put -4 in for X. And let me see if I can do that calculate. It's going to be -7, and then times 4 is 28, and then times -5 is going to give me 140. And then I've got the X minus 6, which is going to be -10. It's approximately 14 times X plus 4 quantity squared. You understand the process. You understand how to fill in these dots. What's the graph of 1 over X plus 4 quantity squared look like? Well, here's X equals -4. This is reciprocal square function. Here's the -4. Vertical stretch 14. It'll look like this. Now we put it all together. And we sketch this graph. Got, well, let me look at the function. Got X equals got X equals negative. And that's about it. So we know what happens near each of these points. Near X equals -4, we're going to want to behave something like this. Near X equals 1, I didn't do that, but it's going to behave like this. Okay, it's going to tend to go like this and up like this. Y-intercept is problematic. Like it's negative because you get X minus 6. Okay. If X equals 0, you get -3 times 4, which is -12, times -1, which is 12, divided by -6 times 16, which is -96. -12 over -96 is ballpark 0.1. Okay. So at X equals 0, your denominator is a lot bigger than your numerator. So you got a Y-intercept down here. Y equals, if I've got this right, -12 over 96, numbers you get if you just do this straightforward, but that's -1/8. So there's your Y-intercept. Now you can see that it makes sense that this graph, the Y-intercept is negative, so this would have to go down below the X-axis. So maybe I have this upside down. Anyhow, you do the end behavior. If X is a big negative number, all these are big negative numbers. You have 4 big negative numbers on the top and 3 on the bottom. That's a total of 7 big negative numbers that you're multiplying and dividing, which is going to make the thing negative. But I think maybe I did something wrong here because it's got to be negative over here. So I think maybe this one would have been like this. So I'm going to say, okay, we come up here from negative. It probably turns around, goes down like this. Then it comes up through here and up through the x-axis, back down through. Then it comes over here like an asymptote. And then it comes down like this. Then it turns around and goes up toward infinity. And there's your graph. In pretty much a lot of detail. How did I get 14 here? X is equal to 4. No way I get a negative out of that. Oh yeah, I do, because of the -6. This actually should have been like -4. And the graph would have been upside down here, so, you know, make little errors, but then you put it all together until things make sense. Okay? So there's a lot of detail, and the reason I like the detail here is you don't need all this detail to do what open math tells you to do. And if you get the graph right, it's okay. But you should be able to answer a question like this if I should ask one. Okay, I won't ask that. That's kind of a hard question. I wouldn't ask a lot of those on an exam, but I could say, here's your function. What function is this close to when x equals 6? Okay. Now, if you just follow the algorithm open math gives you, you're going to find the end behavior. You're going to find the zeros of the numerator and the zeros of the denominator. Zeros of the numerator give you points on the x-axis. The zeros of the denominator give you vertical asymptotes. Now, there's a little more to it. And you know, there were some problems on the homework that people made mistakes on by not noticing that there's like an x plus 4 in the denominator and an x plus 4 in the numerator. Because that's a removable singularity, as open math explained to you. Okay? And I can explain removable singularities. If you miss the removable singularity, I'm not going to regard it as something I have to penalize heavily. But, you know, there's a penalty. A couple of points on a 10-point problem. Okay? And then I write a little note complaining about it. Okay? Really not complaining, reminding you, okay, there's a movable singularity. If you're going to take a fairly rigorous calculus course, you're going to have to be aware of those things. And since this course is pre-calculus, we want to prepare you for calculus. Now, most of you probably aren't going to be taking a really tough calculus course. So some of this is going to be something that bothers you a lot. So I don't spend a lot of time on it. If you're going to be taking the really tough calculus course, then you're going to understand. And if you're not, still worth trying to understand because it makes your brain strong. Okay? But again, the whole thing about removable singularities is not going to make or break you in this course. It's worth noting. Okay. Now let's move on to the table. And this is about all I want to say about rational functions. I did some algebra and just how to add and subtract rational expressions in the MDE class, support class. You probably want to look at that because you're going to probably have occasion to have to do those things. And it's actually fairly simple, 20 some minutes, not as much as 30. Video that you might find worth the time. Okay. Now, we're going to move on to exponential functions. As I say, rational functions are one of the things that's somewhat complicated. Okay. It's important to be in the final. Probably something a little simpler than what I've got here. I just want to see if you can identify the zeros of the numerator, identify the zeros of the denominator, and then do what makes sense. Sketch the graph. And if you're not doing that, if you did the homework by rote or something and didn't write stuff out, you really ought to go back and write stuff out. So you have something to review. You take the flight. Okay. Preparation for this test was much better than it was for the major quiz. Okay. And if you get that much better at preparation by the final, I think everybody here is going to come out okay. And remember, if you want me to let you know a little bit more about how you did on the exam, everybody, I think, can improve this because the stuff with exponential functions is not that hard, especially if you know what the rules are for exponents. That out to one thing that you can easily review. Okay, so we want to make table and sketch graphs for y equals b to the x. B equals 2. If you got to use a calculator right now, evaluate 3 squared, go ahead, but you're going to have to do it by hand. You're going to have to show me details of these calculations. If I ask, punching it into the calculator is totally this course. If you don't understand the rules for exponents and dealing with fractions well enough to do that, you don't understand arithmetic well enough to understand this course very well. Okay? And you can. Everybody has the aptitude to do that. Don't sit back and punch buttons in the calculator. For today, it's okay. You know, some people to evaluate these things. That's what open math tells you to do. I think open math wants people not to understand arithmetic either. It's not open math. Individuals write these things. I don't agree with the idea of using a calculator to do simple arithmetic. Okay, obviously there are places where you need a calculator. Okay, well, I'll get off my soapbox. Okay, you got -2, -1, -1/2. Who gave you those numbers? You should know them. It's the numbers you naturally get when you subdivide that rectangle for an exponential function. Okay, actually, not an exponential function because we do have a problem. Okay, this -1/2 doesn't occur when you subdivide your intervals for an exponential function. You only get this one, don't get this one. Get this one and this one. That's all you use of the exponential function. I think everybody understands that. We're going to see why. Okay, if x is -2, y equals -2 squared, not negative of 2 squared, but the whole -2 squared, which is what? -2 to the negative. Another thing you got to do that I don't always do is I know what you're doing correctly. This is b to the x. This is 2 to the -2, -2 squared. Okay, 2 to the -2, which is 1/2 squared, which is 1/4. I want to see that. I don't want to see the result of punching in the calculator, and I don't want to see a decimal there. We're dividing 1 into 4 pieces. And that's how we get the graph that we learn so well to construct. Okay? So even if both the math tells you to use your calculator, do this first. And do your calculator and see that everything reconciles. It's okay. Don't rely on the calculator. Do these numbers because you won't understand the functions. Okay? Okay, -1/2. 2 to the -1/2 equals 1/2 to the 1/2 equals what? Two to the 1/2 you can't do. You don't have a clue how to do that. You can't have a clue how to do that unless you've had a second semester of a fairly strong calculus course and learned about Taylor series and a bunch of other stuff. It's kind of hard even for second semester calculus. Okay, it's feasible, but it's kind of hard. So we don't do that. And when x equals 0, please don't put down 0 here. Put down 2 to the 0, which equals 1. If you don't know your rules for exponents well enough to know why, and that 2 to the 0 is 1, you need to work on that. Because again, you got a distorted graph. It's not going to look like an exponential graph if you got a 0 here. It doesn't make any sense. I explained early in the course why this makes sense. 2 to the 0 should be 1. So you might want to review that, but at least take my word for it. Okay? There's another one we can't do without a calculator. So we ignore it. 1. No, you know the 2 to the 1 is 2. For 2, you get 2 to the 2nd, which is 4. So now these lines here that did stay very straight. And we have values from 1/4 up to 4. Well, we can do what we've always done. We put y equals 4 here, and then we start subdividing. Here's y equals 2. Y equals 1. Y equals 1/2. And way down here, y equals 1/4. So now we can construct a graph. When x is -2, y is 1/4. That puts us here. When x is 1, -1, y is 1/2. That puts us on the 1/2 line. When x is 0, y is 1, puts us on the y equals 1 line. Then we're on the y equals 2 line. Then we're on the y equals 4 line. And there's our familiar graph of the exponential function. And if you want to relate this, oh, there's your 4x4 rectangle. Okay. So this one is a graph that looks like this. Okay, now let's go to b equals 2. B equals 3, I'm sorry. That gives you y equals 3 to the x. Okay, using the same x values, I get 1/9, 1/3, 1, 3, 9. Now, if you just write out the details, which you need to do, if you do your homework and haven't written out those details, you're shortchanging yourself, if you're missing something you're going to need to know. You need to do it. It only takes a minute to write all this stuff out. If you don't know it and have to stop and think about the rules for the exponents, then, well, you need to do that too. Okay? Then you're going to need a line for y equals 9. You're going to need a line for y equals 3, which is 1/3 of 9. So you cut this interval into 3 pieces like so. And right here is your y equals 3 line. And you're going to need y equals 3 because of the 3. And you're going to need y equals 1, which is 3 times as close to the x-axis. So it's kind of like what you do with the squaring function. But you're making things 3 times as close, which is a little tougher than cutting of the path. Okay? And then you're going to have y equals 1/3. Here, and y equals 1/9, which is so close to the axis on this scale, I can't even draw the line. Okay? The chalk marks would be too thick. Still, we can kind of fudge that. Here's our x equals 2. Here's our x equals -2. Here's our x equals -1. And x equals 1. And I'm going to have a point here. And I'm going to have a point here. And I'm going to have a point here. And a point way down here. And a point so close to the x-axis, you can't even tell for sure that it's above the x-axis. But it is. And no matter how big, well, no matter how far you go into the negative numbers, you're still going to have 1 over some power of 3, which is going to be greater than 0. So this thing never hits 0. Okay, so we then sketch the graph. It looks a whole lot like this one. If we do it to scale, though, y equals 4 here. If we wanted to compare this graph to this one, we'd have to go up to y equals 9 to get this graph. Well, let's just look at what this tells us, because there's a very important function that we can talk about starting right now. Here's x equals 2. Here's x equals -2. I'm going to put y equals 4 here. And then y equals 9 is a little more than twice that far from the x-axis. Here's y equals 9. I know that the 2 to the x function goes through to 0.24. I know that both functions go through the point 0, 1. Okay, there's 0, 1 here, there's 0, 1 there, because whatever your base is, you raise it to the 0 power, you get 1. Any b to the x function goes through the point 0, 1. Now, if you vertically stretch it, flip it, do anything, there's that change. But if you do the toolkit function, the basic toolkit function, okay, well, y equals 1 is going to be like here. So without drawing all the subdivisions, because that would get confusion, that would get confusing, is these points mesh with these points in a kind of complicated way. Would be hard to do it, but it's not really necessary. We know that you're really close to the x-axis over here, so I'll just kind of fudge it and say, okay, there's our graph of two to the x. Then, well, y equals 3 to the x goes through the point 2, 9. It goes through the point 0, 1, and it starts really close to the x-axis. So it comes over here, and then it gets pretty steep. Now it's below the graph of the 2 to the x function over here, because 1/9 is less than 1/4 and 1/3 is less than 1/2, right? So when you do the reciprocal by, that you have to do for negative exponent, you're going to get lesser values for this one than you do here. But as soon as you pass x equals 0, now you're doing positive exponents, and these numbers are going to be smaller than these numbers. Okay? So the graphs look like this, and you should be sure. This is not overly complicated. You make your pictures. You should sit down and make the same pictures. Okay? After you get the hang of it, it doesn't take long at all. And it's worth the time because it reinforces something you're going to need to know. Now, really important thing here. There's another function. E to the x. Okay? This function has some really important characteristics. It's maybe the simplest function there is to do calculus with. It's a little involved to do calculus with this function or this function, but it's really easy to do it with this function. So one reason to love the exponential function is it's really easy to do calculus with it. E stands for exponential or Euler number. That's not like oil can, that's like EULER, German pronounced oil. Okay, please turn. I don't remember. It's been a long time since I've talked to him. I don't remember what his accent was. I think he died in the 1850s. Yeah, I wasn't very old then. Okay, y equals e to the x. I'm just guessing about the 1850s. I didn't go to school. Y equals e to the x. E is approximately 2.7, which is closer to 3 than it is to 2. Store this away, especially if, as a few of you might well do, get up in an engineering calculus course. I tell you, there it is. it's not hard to remember because you got that 1828, 1828 that repeats, but it doesn't repeat again. The next few digits are not 1828. Okay, it's a non-repeating number. It's irrational. It goes on forever. Well, okay, for our purposes right now, 2.7 is close enough to understand that this graph is going to lie between these two graphs and probably a little closer to this one. If you square 2.7, you get about 7.1, 8.1, sorry. And it goes up to about here. Okay, E is between 2 and 3. Y equals e to the x is here. If you plug in x equals 1.6, you've got an e to the x button on your calculator. It'll tell you what e to the 1.6 is to whatever number of significant figures your calculator shows you. Okay? That relies on the Taylor theorem, Taylor polynomial as well. That is like 2 to the 1/2. Okay. And you won't know how to calculate that, although I could give you the formula for it. Not hard to understand the formula. Okay. If you put in 1.6, it'll tell you what the thing is, okay? Now, if you put in a number just a little less than 1.6, say just 1.5 and 1.7, a little less than 1.6, a little more. And you get the coordinates of those 2 points, do a fundamental triangle. The slope of that fundamental triangle will be very close to what you get when you evaluate e to the 1.6. And the slope of this curve is equal to the value of the function. So this distance here, that's the value of the function, right? And the slope of the curve, you can see what the slope of the curve ought to be there. If the curve is drawn accurately, the slope of the curve will exactly equal how high the curve is. That's kind of a useful thing. It's really useful. So it makes calculus so simple. Okay. All right. Well, there we have it. If you do the I can slip this in here. One half squared is 1/2 times 1/2, and that's 1/4, right? 1/2 to the 1 power is 1/2, 1/2 to 0 is 1. So these numbers are really easy. And then you got to do 1/2 to the -1, which is 1 over 1/2, which is 1 times 2 over 1, which is this. And if you just know how to manipulate fractions and know the arithmetic that you learned in 5th grade, you can get these numbers. What happens if you graph these? You get -2, 4. You get 2, 1/4. You get 1, 1. And the rest of the details would prove to you that this graph is just a reflection of the 2 to the x graph across the x-axis. Okay? Because what? Because the y values are the same values of x, equally spaced. The y values are going to be the same as the y values over here but in reverse order. Okay, so f of negative x would equal f of x or whatever. I don't want to write that down. I don't want to confuse the issue, but there you have it. You could do then just to kind of extrapolate it a little bit. If y equals 3 to the x is here, then so this purple graph is y equals 1/2 to the x. Might be hard to read. This graph is y equals 1/3 to the x. And it's a nice, pretty picture, and you're going to see a picture very much like that in your textbook. Okay. Well, that's the first thing you need to know about exponential functions, and that should be a very easy thing for you to do and understand. And please, when you do these things, unless you've got some really weird numbers for b, if you can do the arithmetic, it's possible to do the arithmetic by hand, do it by hand, write it out. You'll understand things that you're going to need to understand when you start using these functions. And I'm going to pause for a minute. Okay. So you know how to construct the shape of an exponential function. End up looking something like this. Okay, so we put that inside of grid. It's pretty much what it looks like. Okay. This could represent the 1,000 times 1.05 to the x. This is a value. Let's instead of x, let's use t here. I think I've done this before. Everybody's this is a value of if this line, which is normally y equals 1 when you construct the toolkit function, you're multiplying it by 1,000. So you can construct your toolkit function. You got 1,000 in front of it, where you label that y equals 1 point as y equals 1,000. Because if this equals 1, as it does if t equals 0, right? 0.05 is 0 is 1. So you'd have 1,000 times 1. So you'd have 1,000 here when t equals 0. That's your y-intercept. A recording. Thought I was, I'm never sure. Okay. The screen should show me, but it doesn't. Gotta check this over once in a while. Okay. So anyhow, you got that, right? Okay. Now, doubling time is about 14 years. Okay. So in my adult life, I've seen 4 doublings. Okay. If 5% is right, and that's kind of about a good approximation. Okay. Uh, you know from the construction of the exponential function that each of these lines is twice as close to the x-axis as the one before, right? Which means if you start from here, this line is twice as far from the x-axis as this one, and this one is twice as far as this one, and this one is twice as far as this one, right? So from here to here, your y value is doubled. And from here to here, your y value is doubled. Okay? So with the standard construction, our standard construction, I didn't draw it quite correctly, but these doubling times are all the same. You understand that because you know how to do this construction. I don't have to give you a bunch of algebra and a bunch of analysis. Uh, that's a big deal. The way we calculate the doubling time, how do you do the inverse function to the exponential function? You swap x and y. Quickly. If this is your exponential function. Now, this thing here that you get when you swap x and y and you get the logarithmic function. Okay. Now we're out of time, so I'm not going to get too deep into the development of this. We're going to see it late this week and next week. And what that logarithmic function is. And the thing that's really handy is you have a button in your calculator to do the natural log function. And to do a log with any other base, you know what I'm talking about, but it's easy to do that too. Okay. That's how you determine the doubling time. You use a logarithm to solve a certain equation. And the rules are very, very simple if you reinforce them when you see them. Okay. So please do everything you can to reinforce what you're learning. Stuff we do in exponential functions is a good opportunity to solidify your grade. Okay. So work hard at this and write things out, please. You got another strategy for learning and retaining things, and you know that it works. You can ignore what I'm telling you, but most people at this stage of their education don't, and you would probably profit heavily from doing what I recommend. Okay.